What's going on, guys? Welcome to Ask Melissa Maribel Live, where you tweet me your questions for a chance to get them answered in my next live show. Thank you so much for being here. So excited to kick off this new live session, this new show overall. And today I'll be going over a lot of topics, especially if you are in AP chemistry or in general chemistry too, the second part. This is going to be extremely beneficial to you. I'm talking about balancing redox reactions, so that's going to be a little bit of general chemistry 1 and AP chemistry, as well as galvanic cells and finding the standard cell potential, finding cell potential, cell notation, electrochemistry, so much. So it's a jam-packed lesson today, and I'm excited to share what I have for you guys. I have Ryan in the chat who says, hello, thank you so much. You're welcome, Ryan. I actually chose Ryan's tweet, and I completely changed that into a detailed lesson, which I have here, and I'm excited to share that with you. I also have in the chat saying, hey, hello, happy you guys are here, so happy you guys are with me and that we're live. Why don't we go ahead and go to what we're going to be talking about today. So like I said, it's all about electrochemistry as well as balancing redox reactions is what we're going to start off with. So for everyone who is watching the replay, in the description box, as well as in, I think, a comment, I'll pin a comment putting all of the different timestamps as to all of the topics that we'll be going over. So if you want to rewatch this and see this again, you can instantly just go to whatever topic you need. So yeah, and I see more people. Awesome. So I have Koti saying hi, Jennifer saying I wanted to drop AP chemistry and then I found out your class. Oh, okay. And now I love chemistry. So happy to hear. So happy to hear. I'm glad that I actually get a lot of you guys saying that you now love chemistry and you now find it fun, which is awesome to hear. So thankful for that. All right, let's start right in. Let's jump right in and go to balancing redox reactions. Okay. So with balancing redox reactions, it's going to be super important to know the order and how everything works, especially how to find oxidation numbers. So oxidation numbers, what they allow us to do, it's not, I wouldn't necessarily say it's the charge, but instead it just allows us to see how many electrons are being lost or gained to understand, okay, is this reduction or oxidation? So that's what we're going to go into right now. What you see on the screen are all the different rules and all the different steps that we have to do to balance a redox reaction under acidic conditions or in an acidic solution. And we'll go over a basic solution as well, or basic conditions. And you'll note that there's really pretty much 2 additional steps. And I actually would even say that there's technically 1 additional step to the acid conditions steps. Okay, so it's like a couple more steps besides this. So why don't we just start and we'll jump right in. So oxidation numbers, let's just review all of our oxidation numbers and what we have. So like I said, oxidation numbers help show how many electrons are either gained or lost. So, and that'll help us determine if it's oxidation or reduction. And this list that you see on the screen, and I'll show this. So, and by the way, if you guys haven't downloaded the free survival guide just yet, I highly recommend checking that out. That link is in the description box. And like I said, that's completely for free. I also put the oxidation numbers and a lot of the formulas that you will see that I'm using all throughout this lesson. So, and that's also for general chemistry 1 and 2 and AP chemistry. Okay, so make sure to check that out. I'll put that in the chat right now. So if you haven't downloaded it, I highly recommend it. Save yourself some time. So awesome. So why don't we just keep going? And our oxidation number, the first type, is whenever you see an element in its solid state or really just by itself. So like in this case, we have an example of Na, and it's in its solid form. The oxidation number would then be 0. And then, okay, what if we have a diatomic molecule? Well, in this case, diatomic just means that it exists in pairs. So let's say Cl2, F2, O2, right? All of these are existing in pairs. And those are typically in their gas state. So this would have been an oxidation number of 0. And then we'll keep going down the list. And the main ones that I often see, and that we'll see today, is one element that has a charge. So if, let's say, for example, we have iron and it has a 3+ charge, that charge is then its oxidation number. Okay, so that's going to be really helpful to note with these. The next thing is anything in elements, and actually, sorry, I skipped one, hydrogen. Hydrogen is super important to know. Whenever it's within a compound, not just by itself, it will have an oxidation number of +1. Same thing goes for elements in group 1. That's going to also have an oxidation number of +1. Elements in group 2, and that's once again in a compound like magnesium, this is going to be +2. Oxygen, very important to note, oxygen is always going to be a -2 oxidation number. And lastly, if you can see at the bottom, a halogen within the compound is going to be a -1 oxidation number. Okay, and like I said, this is all in the survival guide, so don't worry about writing this all down. So let's keep going. Let's find our oxidation numbers first. This is what we're trying, this is actually our redox reaction that we are trying to balance under acidic conditions. And then I'll also do the same thing for basic conditions. So let's just start off with our oxidation numbers. And then note that, okay, I'm going to instantly go to all the ones that have charges, and that's a lot easier because now they really told you what the oxidation numbers are. So for iron, that's going to be our 2+, and then this iron over here on the product side is going to be +3, and then manganese is going to be a +2. So that's exactly what we'll see. Now, it's going to be a little bit different when we're looking at something that is within the compound. So like let's say here, for example, we'll note that the only oxidation number that we actually know is oxygen. So oxygen's oxidation number we stated was a -2, and that's where we're going to start with. We don't know what manganese's oxidation number is. That's what we're actually trying to figure out. So we will use a little bit of algebra, not too complicated, I'd say, and I'll walk you through it, so don't worry about that. So, okay, how this is going to work is we said that oxygen has a -2 oxidation number. Now, how many oxygens are within this compound? Well, there are 4. So we would actually multiply 4 times the oxidation number of oxygen, which is -2, and then that would give us -8. And then the next step is to actually build an algebraic expression, or an equation really, to figure out what manganese's oxidation number is. So that's exactly what we did here, where I don't know what manganese is. I'm going to place an X here, and then I'm going to bring down that -8, which we found previously. And then it has to be set equal to the overall charge of this compound. So here you'll note that the overall charge is -1, and that's exactly where I got that -1 from. Next step is to solve for X. So we want to get rid of this by adding 8 to both sides. These two would then cancel, giving us X is equal to +7. And those are, oh, this should have been positive. Sorry about that. This should have been positive. Okay. So positive, manganese would have been +7, and then oxygen we said would have been -2. Okay. And by the way, this -8 was only there to help us figure out what manganese's oxidation number is. Okay, so that's kind of what we're looking at. All right. Next step. Now that we figured out all of our oxidation numbers, we're going to write our half reactions. So what half reactions are, it's essentially just breaking up this redox reaction into 2 different reactions. One that is the oxidation side, and the other is reduction. So how you can know, and how I like to think of it, how I decide which one's oxidation, which one is reduction, think of it this way. Oxidation is going to become more positive, while reduction is going to become more negative. Okay, so that's exactly what we see here. So this goes from a +2 oxidation number to a +3. So that just became more positive. And then that's where I got, okay, that must have been oxidation. And then next, what about reduction? Well, reduction has to reduce. And this would have been a +7. Now it reduces down to +2. Another thought is kind of like it becomes more negative is how I also like to think of it. Now, one little thing that I will mention, and this is going to come into the other parts of this with electrochemistry, is oxidation is actually losing electrons. Okay, it's like opposite of what you're thinking. And reduction is gaining electrons. How I personally like to remember this is, let's say with reduction, since you're gaining electrons, think of it as electrons are negatively charged. So if you're gaining more negative people in your life, which I hope you're not, that's going to make you more negative and make the overall oxidation number negative. Okay, and then now with oxidation, if you are losing that negativity, you're then becoming more positive. So that's personally how I remember it. Oxidation, just think of it as you lose electrons. Reduction, you gain electrons. Okay, now that we know this, let's continue and actually write our half reactions, but we need to figure out how many electrons are being gained or lost in this overall redox reaction. Ryan just said oil rig. Exactly. So oil rig is a good little mnemonic device that I highly recommend if you don't want to think of it the other way. Another one that I have heard, which is kind of adorable, is Leo the lion goes grr. I don't know if you guys have heard that one. I think I learned that one in high school or something, but yeah, there's that one too. Now, with finding electrons for each half reaction, what we're going to do is we're going to look at the oxidation numbers from our products and then our reactants, because we're going to subtract them. So essentially, this is what I want you to think of. Your electrons are equal to the product's oxidation number minus the reactant's oxidation number. And of course, we're just looking at that specific one. So like, I'm only looking at iron for oxidation. I'm only looking for manganese. So I'll give you an example. In this case, let's say if we're just looking at the electrons here going from our products, and I'm just looking at oxidation. So this would have been 3 minus that 2. So there I have 1 electron. Okay, so that's 1 electron. Now let's look at reduction. I'm going to do the same sort of concept, but instead I'm going to do 2 minus that 7, which would give us 5. And then I want to make a little note here. So after we see that there would have been 5. The negative, by the way, I know that this technically would have been negative. It doesn't necessarily matter. The reason for that is because electrons are negatively charged regardless. So just note that it really just tells you how many electrons are either being gained or lost. And in this case, we have 5 electrons. How we're going to write this first oxidation half reaction is I'm going to start off with just whatever reactant I had, which was iron. I'm going to bring down this product, okay? And then next, I'm going to add this 1 electron on the product side. So oxidation, that's where you're going to add electrons to the product side, while reduction, add it to the reactants. So reduction, reactants. All right, that's what I want you to think of. And then that's what we'll have here with our reduction half reaction. Okay, so these are our half reactions. We still have plenty to go with balancing, all right? So bear with me. So now those are half reactions. The next step is to balance the elements other than oxygen and hydrogen. The reason for this is because when we're balancing these redox reactions with under acidic conditions or basic conditions, we have a specific thing that we do when we're trying to actually balance the oxygen and the hydrogen. And we'll see that in a second. So we'll see that we'll add water, or sometimes we'll add H+, which is essentially acid. And we'll get to that, but it's a little bit trickier. So instead, what I want you to look at for right now is just, do we have everything besides oxygen and hydrogen balanced? And yes, we do. The reason for this here, right, we only have 1. We're just looking at the coefficients in front. We only have 1 iron on either side, and we only have 1 manganese on either side. So that is balanced. Next, we have to add water to balance out the oxygen. So what I'm going to look at is how many oxygen, this is the only one that has oxygen. So how many oxygen do we have on the reactant side? And we have 4. So since we have 4 oxygen and we need 4 more to, balance everything out, that means we have to add 4 waters. So you will always add the amount of waters, you will always add the amount of oxygens you need as waters, if that makes sense. So I needed 4 more oxygen on the product side. That's why I added 4 waters to balance that out. And then think of it this way, we would have distributed, right? And that does give us 4 oxygen overall. But now the hydrogen is not balanced here. So now what we're going to do next is balance out the hydrogen by adding H plus on the opposite side. And let's see how many H's we're going to need. This is going to be 4 times that 2. So 4 times 2 gives us 8. So we'll put 8 H pluses on the reactant side. Okay. So now that that's set, let's keep going. So those so far are the 5 steps. I'm going to keep going. There's a few more. Next step is to always make sure that you balance out your electrons. So the reason why I don't do that in the very beginning, you'll see this in a second, is sometimes you have to multiply the entire half reaction and it messes up things. Okay, so that's why I always leave it to step 6 or towards the end after I really balanced the hydrogen and the oxygen. So balancing out our electrons, they have to be the same on both. So what I'm going to do is note that there's only 1 electron here, but there's 5 on the reduction half reaction. So I have to multiply this entire half reaction by 5. And then that's, here, let me make this prettier, 5. So then we'll have to distribute this, and we'll see that, I actually had it, that's right. I'll distribute that, and then everything now has a 5 in front. Okay, almost there. So one of the last steps is to add both of your half reactions together. And we'll note that anything on opposite sides, so let's say if something is on the reactant side and the other is on the product side, and if they're the exact same, we can cancel them out. You'll note that with your electrons, you can actually cancel those out since they are on opposite sides. Okay, and then here, what I'm going to do is I'm going to add everything on the left side together, which is the reactants, right? All of these are going to go on one side. And then everything on the product side or the right side will go together and combine. And then we're going to have this long reaction that we have now. And then, as mentioned, our electrons canceled, right? Our electrons canceled. And then this would have been our answer. That's only if it's an acidic condition, okay? And how you can actually tell that this still has acid in it is due to that H plus. So if you ended with H plus and it has to be under basic conditions, then you didn't finish this overall question, okay? But however, if it's just asking for an acidic condition, then you did. Then H plus remains, yep, you're good. So this would have been our answer for an acidic condition. Now let's look at what you would have needed for a basic condition, just continuing on with this process. So these are all the steps. And by the way, everything that I am mentioning and all these, pretty things that you're seeing on the screen, that is actually some of the pages from my Redox reaction notes that I have for you guys that I've made. And what I want you to think of it as, it's basically, goodness, it's so many hours of tutoring that is reduced to a very, very low price. And I even have a back to school promo code that I've been doing, and it's literally back to school. That's the coupon code. So if you guys would like to get the Redox reaction notes, it has so many examples with how to find oxidation numbers if you're struggling there, how to balance, and there's more examples of balancing redox reactions, of how to find the oxidizing agent, how to find the reducing agent, and so on. So all the different topics on redox reactions, and I just put that on the screen so you'll see that's the promo code. That also works with all my other notes that are in my store, so make sure to check that out. Okay, so let's keep going with balancing under basic conditions, and you'll note that the main difference, this is where we left off, right, for acidic conditions. So what we'll do is you technically have 2 steps, really, you can combine them, but the the 8th step is we're going to add OH minus to neutralize that H plus. And what this is essentially doing is H plus is acid, OH is base. Putting those two together makes a neutral reaction, so it neutralizes each other, and that's what we want to see. So let's continue. Okay, so this is where I left off from the last one. All I'm going to do is I'm going to add OH to both sides. And how many OHs do we need? Well, it's the same amount of H pluses we had. So we had 8 H pluses. That's why I added 8 OHs on both sides. Make sure to add it to both sides because that balances it out. Next thing is you're going to combine the OHs and the H's to form water. So both of these, as you'll see, 8 OHs and 8 H pluses, those will combine to form 8 waters. Almost done. You'll note that we still want to cancel things that are the same on either side. So we have 8 waters and 4 waters on the opposite side. Those will then subtract. And this is going to subtract to 4 because that's only 4, right? That 8 minus 4 is essentially what we're doing. And we now have 4 waters on the reactant side. And this would have been our, this should have been a 4. There we go. And we're still left, by the way, this is another good note to just see, is this under basic conditions? Yes, because of that right here, it's showing you the arrow, because of this OH, right? That's what hints and tells us that it's under basic conditions at the end, and you did it right. Okay, hope that's making some more sense. Let's keep going to more electrochemistry concepts, and we'll get into a voltaic or galvanic cell. By the way, I've heard either term. It really just depends on your professor, but we'll go over, I'll call it a galvanic cell. Really doesn't matter. They're both the same thing. Okay. Now, when we're talking about a galvanic cell, a voltaic cell, what I want you to imagine or think of is a battery. Okay. So a little maybe AAA battery or something like that. That is a galvanic cell. And what's essentially happening in that little battery is there's chemicals that once they react, which is actually a redox reaction, once those two react, then electricity is able to be produced, or a current can then come from that chemical reaction, which is pretty amazing. Your car battery also does this too. But that's the general concept. And I'm going to dive real deep into just what all of this is and all of this means. But this is kind of like my simple way of saying, okay, and in case you're not too sure what in the world a galvanic cell is, think of that little battery that you've seen before. Chemicals react together, and it then allows us to produce an electrical current or electricity. Okay, that's the general concept. Okay. So, as I mentioned, a common example was a battery. The next thing is it's spontaneous. Now, what I want you to think of when we're talking about something being a spontaneous reaction versus a non-spontaneous reaction, what it essentially means is if something is spontaneous, then it's going to happen on its own. So think of it this way. If we were to have some chemicals, actually even in that battery, that those two chemicals that are there reacting will then go to the finished product, or meaning you have reactants and then they proceed, how am I trying to say this? Sorry. So we have reactants and it proceeds to the forward reaction, meaning it will just occur. It will happen. Okay. So that's what it's essentially stating with spontaneity or something being spontaneous. It really just means the reaction will occur. Okay, and it will occur on its own. However, non-spontaneous, that will not occur on its own. A reaction will not occur on its own. Instead, it will need some sort of push. So remember, anything that can speed up a reaction would normally, you'll see this with heat, right? Some sort of heat, some sort of increase in temperature, possibly a catalyst, and so many other factors that we won't go into with this, but that's another section to talk about. But that's essentially what I want you to think of when we're talking about spontaneity, something being spontaneous versus non-spontaneous. And I think Ryan just said, what happens when the salt runs out in the car battery? That sounds like a dangerous game. So we'll get into that actually. Okay. That's pretty cool. I'm glad you brought that up, because in a galvanic cell, which we're going to cover, you'll note that there's a salt bridge. That salt that's in the battery is acting as the salt bridge. And you'll actually note, if you've ever seen any like buildup, any like charge buildup on that battery, that's because the salt is running out. And that's not a good thing. That actually can cause a lot of problems. The reason for that is because that salt that is inside the battery is actually allowing that electricity and that current to flow. So we'll get into all the specifics and all the details, but that's essentially what's going on at a glance. Okay, so it just allows everything to regulate on its own and actually flow correctly, instead of just buildup occurring, and sadly your car battery is then dead, right? So I've had that happen before, which is not fun. But okay, let's start off with a galvanic cell. And let's say if we had something like this, remember we're going to have a redox reaction occurring, right? That's the reaction that is going to combine together and react and then form that electrical current. And what we're going to see is oxidation has to occur, right? Redox, the fact that it's in the name redox, right? That's going to be reduction and oxidation. Oxidation is going to occur at the anode, and the reduction is then going to occur at the cathode. How I remember this was red cat, okay? Just red cat, that told me reduction cathode, okay? So why don't we write this in the half reactions? I really did that for you. And just in case you need a little bit more practice with that, here we'll see, let's say if we actually wanted to look at the oxidation numbers. Remember, this is our charge, so this is a +1. Any metal or any really element on its own in its solid form, and I know I didn't put the phases here, but assume that this copper would have been in its solid form, is going to be an oxidation number of 0. And then same goes here with silver, and then copper would have been a +2. Okay, and then once again, remember that if we're looking at oxidation, the one that's being oxidized is this copper, and this is going from 0 to 2+. It's becoming more positive. That's why it's oxidation. Reduction must then be the one reducing. So this is +1 going to 0, and that's why I put our reduction there. There are 2 overall electrons moving here, and that's what you're saying here. Okay. So let's get into how this all works and get a little bit more into, conceptualizing everything. So here we have our anode and our cathode. Okay. So our anode and our cathode. And once again, we'll see that, okay, well, oxidation is occurring at the anode and reduction is occurring at the cathode. What you'll note here is we actually have a solution that's already made, already prepped in those beakers or in that anode and cathode. So we'll note that, okay, our anode has copper nitrate and our cathode has silver nitrate. All right, and I'm just putting the half reactions there. The next thing is we're going to place some sort of metal, some sort of piece of metal in our anode and our cathode. And I noted everything that in your anode, we'll place the copper metal, and then silver will go in the cathode. So that little square or rectangle really just means it's a piece of metal, okay? Next step. So now that we have that metal, we're going to add a wire. And what I want you to remember is, remember the properties of metals. So metals are good conductors, right? Good conductors of electricity. And essentially what is happening here by connecting that wire, we're now allowing for the flow of electrons. So that's what's next. Our flow of electrons is then going to allow us to then produce that electrical current or electricity. And that's something that I want you to actually understand is, even, how lit this whole entire room is, this is electricity, meaning there are electrons moving back and forth, and that's allowing us to have light. So that's pretty awesome, right? I mean, just thinking about it as how does light actually form? It's electrons that are literally moving. So that's the general idea of it. I had Ryan ask, does it matter which solvent you choose for the ions, or do you have to choose one that cancels with the charge? So what I typically, this was given, here, let me go back to the solvents. Here we go. So the main thing is, and we'll actually see this in a second, the reason why I chose these solvents, or why this was even given to me in the question, was the fact that we wanted to choose copper metal, right? And that's actually what we're seeing here. We have copper metal and we have silver metal. So in the anode, we mentioned that we had to have copper, so that's why it's in front. And then for reduction, or in the cathode, we had to have silver, which that's why it's in front. We'll note in a little bit that our salt bridge is actually going to contain that same ion of nitrate. Okay, so that's how you're pretty much figuring this out. So like I said, your anode is going to have that same metal, and then your cathode is going to have that same metal in front. How I'm then figuring out what the next chunk of this is, what the ion is based on whatever salt bridge I have. And like I said, once again, that is a salt, right? So a salt is then an ionic compound, just making it a metal and a non-metal, which I'll get into that in a little bit, okay? But that's the general concept. That's how you can figure it out in case they didn't give that to you. All right. Let's keep going. Take a quick little sip of water. Oh, let me go back. All right, so this next one is very, very important to note because I always see this on like quizzes or exams or even just homework questions in general. So what you will be asked is you're going to be asked where or how is the flow of electrons. That's essentially what the concept is. Like they're going to ask you, here, how do the electrons move? So sorry, I wrote that down. I was like, where is it? So yeah, how do the electrons move? So how do the electrons move? They move from anode to cathode, and that's going to be the case for voltaic or galvanic cells, same thing. Okay, so that's what I essentially want you to just to know and think of. All right, that will come up, even if you're taking AP chemistry, and that's like I've actually seen that on an AP test, AP chemistry test. I've seen that multiple times. It's just a common question. I don't know, they love it. So make sure to know that, okay? Anode to cathode, that's how the flow of electrons move. Okay, so as this continues, as these electrons start to produce that electricity by literally moving from the anode, which is now the copper, to the cathode, which is the silver. Essentially what's happening is if we were to put a light bulb or let's say a voltmeter or anything that really measures electricity, by the way, that's actually why if you were to see a light bulb and it actually looks, or even any sort of connection to a light and it tells you how many volts it can go up to, that's what it's measured in. So that's what electricity is essentially, that's the measurement of it, it's volts. So a voltmeter is just anything that can measure that, okay? So it could be a light bulb, it could be literally a little like voltmeter or meter that tracks how many volts are in there. So that's what we can see, and that's what you typically see in your lab. Unless I have actually never did one with a light bulb, that would have been cool, but no, we didn't do that. We just had a voltmeter there. Okay, so let me see if there's anything else I want to mention. Perfect. Okay, so let's keep going. The next step, as all of this is going back, as electrons are kind of in this tug of war, okay, as electrons are going back and forth from copper to silver, what we need to regulate this all is a salt bridge. And let's say in this case, our salt is potassium nitrate. And that's actually what I mentioned before, right? With nitrate, that ion, that's why I chose our solvents as copper nitrate and silver nitrate. So what I want you to think of is a salt bridge allows for the electrical current to flow properly. It also will then neutralize the solution. So that's kind of the main purpose for a salt bridge. As mentioned, if we, like let's say in a battery or really any type of battery, if you were to see some sort of buildup, some sort of like charge buildup, that means that your salt bridge isn't necessarily there. A salt bridge's purpose is to actually remove that buildup and to allow for that electricity or electrical current to continue to flow. So that's the main purpose of it. And let me see. Let's keep going. Okay. So next, what is going to end up happening if you let this run for long enough is I want you to think of this, the anode and the cathode, those pieces of metal, as kind of like a tug of war. So they're fighting for electrons, and they're going to keep pulling each other. Now, there's going to be one winner. So someone has to win, right? So the one that's going to win is the cathode, and that is always going to be the case. The cathode is going to win. And what I mean by that is that's actually the description of how the electrons flow, right? We stated that it's going to go from the anode to the cathode. So that's why silver, in this case, which is the cathode, is then becoming larger. So it gains more electrons, which should also make sense because the cathode is reduction. And what happens in reduction? It gains electrons. And then but then you could also think of it too with the anode. Note that it's actually seems like it's being eaten away a little bit, right? It starts to get a little bit smaller and smaller. And as it gets smaller and smaller, it's actually losing electrons. So as it's losing electrons, that makes sense because it's oxidation. Oxidation is a loss of electrons. So that's essentially what's going on in this overall process. And as mentioned, the cathode is going to be the heavier one, or the one that's stronger in electrons. Okay, it has a stronger pool of electrons. So that's the general concept. That's what main thing. Ryan just asked, is the buildup on the silver? Yes. So microscopic, yes, it is. So I kind of just exaggerated here. Eventually it will become a lot smaller, but yes, it is at a microscopic level. Yeah, like like to the naked eye, no, we can't necessarily see that per se. But if we were to really look at it, we would actually see that it starts to be eaten up. Yeah. So that's the general idea of this, okay? That's the general idea of a galvanic cell. So that should make some more sense. As I mentioned before, it really is just that chemical reaction, that redox reaction, combining, and how we did that, right, was having these solutions and then placing our anode and our cathode, connecting it with a wire to allow that current or that flow of electrons to occur, having the salt bridge to regulate everything, to neutralize any sort of charge buildup that we might have, just to allow for electrons to flow from the anode to the cathode. All right, so those are some general questions that you might see. You might also see them ask you, how to draw it. Now you have a general idea as to where everything goes. And once again, the heavier, I've seen this question as well. I've seen where they ask which one is heavier, which metal is heavier. Well, if it's your cathode, then it's heavier. That's the main way that I want you to approach that, okay? And how do you know it's your cathode? Well, reduction must have occurred. All right, so that's how we're going to piece those two together. Okay. So let's keep going. And something I want to mention, guys, I'm so thankful that I can be doing this for you guys. If you guys aren't familiar with my background, I've been actually a tutor for quite some time, probably over 10 years now, but I understand how how much a tutor costs and how difficult it is to actually find a good tutor. I was on, both sides of there, first a student, then became a tutor later on. So this session is very, very valuable. If I were to look at it, it's over $100. And it's amazing that you guys can actually get this for free and that you guys can actually be educated for free. So it's a beautiful thing. I certainly didn't have that luxury during school, and I wanted to make that available because I understand the difficulty of finding a good tutor and also being in college and not having the means, right? So yeah. Okay, let's keep going with this. Next thing that we're going to go into is how to find the standard cell potential. All right. So we were talking about that voltmeter that was in the middle of the wire between the anode and the cathode, right? So those two, essentially, that's going to allow us to read what our cell potential is. So what that volt is, okay, that amount, and everything is measured in volts right now, okay? So what I want to do is our first step, and typically our main step for all of these, is to find which one is our anode, which one is our cathode, and then go from there. So I wouldn't say that this part is too bad. It's just remembering the formula and remembering, those oxidation numbers, remembering which one's your anode and cathode. And that's pretty much the main thing here. So let's go ahead and look at a little bit of oxidation numbers and then go from there. So I'm going to start off with finding oxidation numbers again. Our silver is going to be 0. Okay, so that's going to be 0 because it's one element in its solid state. Now, the next part, this is going to be a little bit different. Remember that oxygen has to be -2 for our oxidation number. So I'll put -2. We don't know what nitrogen's oxidation number is just yet. Now, I'm going to multiply that -2 by how many oxygens there are, which is 3. So then that would give us -6. Next, we stated we don't know what nitrogen's oxidation number is, so I'll state X, and then that will be set equal to the overall charge of the nitrite ion. Actually, no, it is nitrate. And then this would have been a -1. Okay, so the next step is to solve for X. I'll add over the 6 to both sides, and then X, or really nitrogen's oxidation number, is then 5 plus 5. Okay, and we'll keep going. And then here with hydrogen, that really doesn't necessarily matter, right? We stated that was just +1. That's not going to change. And then aluminum, that's going to be the same exact thing as its charge. And I feel like I accidentally put aluminum. Sorry about that, guys. It should have been aluminum, not a silver. So then this would have been +3. There we go. And then now I'll do the same thing with NO. So we said that this must have been a -2 for oxygen. We don't know the charge, or actually the oxidation number of nitrogen, so I'm going to state X. However, the overall charge of this molecule is actually 0. So just solving this must have been a +2. So this is a +2. And then water, again, this one's a little bit easier because we know each one of these. Hydrogen is a +1 for oxidation number, and oxygen is -2. And then I'm going to keep going with this. So I'm just going to look at the ones that actually changed. So aluminum went from 0 to +3. The fact that it went from 0 to +3, that tells us there was an increase, right? It became more positive. So that means it's oxidation. And then now let's look at the one that, most likely it's going to be reduction. So nitrogen is that case where it went from a +5 to a +2, that reduced. So then that's our reduction half reaction. So that's exactly what we're going to do here. And I would have rewritten everything. This should have been, oh, okay. Sorry about this, guys. This actually should have been aluminum. Just to let you know, this should have been aluminum. But okay, but we'll keep going with that. This still helps with the overall concept. This equation is going to be very, very important, just to let you know. You're always going to see this come up. So E of your cell, and something that I really want to make a note of is that little circle, that little degree symbol, or E0 is essentially what it's called. That just means it's under standard conditions. So there's going to be something just really, really important to know that difference. Whenever you see that little degree symbol or E0, that's going to tell you it's the standard cell potential, versus if that wasn't there, if it was just E sub cell, then that would have been the cell potential. Now, the main difference between these, and by the way, this is going to be really, really important to know, is whenever you see that little E0 or that little circle, essentially the concept is that has to be under standard conditions. What I mean by that, it means the temperature. So it means the temperature is at 25 degrees Celsius, or if we converted that to Kelvin, it would have been 298 Kelvin. Okay, so that's what I want you to focus on. Now, if the temperature is something different, then we would have to use a different formula, and we'll get into that. But that would then tell you it's at non-standard conditions. Okay, so knowing those two. We'll also see that with, if you're in AP Chemistry as well as the second half of Chem 2, you'll see that you're going to need this, or actually even this explanation is going to work for anything that really has that degree symbol, like let's say for Gibbs free energy, entropy, enthalpy, all those types of concepts, okay, which I'm sure we'll get through eventually, okay? So you will see that with Gibbs free energy this time around at the end, just to let you know. Okay, so let's keep going. All right, so a standard reduction potential table must be given to you. There is no way to magically figure out or memorize these numbers. You will not be asked to memorize these numbers, thank goodness. So this has to be attached on your quiz or exam, all right? And if it's not, raise your hand and tell them, where is it, okay? Because there is no way that you have to memorize this. All right, so how we're going to approach this and how we're going to use this table is all of these half reactions are only, and I mean only, in the reduction form. They will not be in the oxidation form. So that's something to be aware of, okay? And we'll get into an example that could be like a trick question, and I'll teach you how simple it really can be, okay? I'll walk you through it. Don't worry about that. So as long as you know that all of these half reactions are in their reduction form, that's what I really just want you to focus on, okay? And you'll note that it will tell us exactly what we need. Like we had NO3 with this whole entire thing, right? This remaining, and that's going to tell us the overall electrode, or actually the E of our cell, our cell potential, standard cell potential, and that gives us 0.96 volts, and that's essentially where I'm pulling everything from, okay? And then same goes with aluminum. We'll see that here. This is going to be a negative 1.66 volts. And then something that I will say to always be aware of is always make sure it looks exactly what you like, as to what you're actually solving for, because there are multiple ones of these. Like there's different charges of iron. Here's a 2+, here's a 3+, same with copper, same with a lot of these. All right. So always double check that that is the correct one. I've seen students miss a complete, page worth of that just because of that reason, even though they knew how to do it. So always double check that. Okay. So let's say if we continued with this, once again, that's supposed to be aluminum, not silver. So, all right. So I pretty much just took out the half reactions from the table, and I really put their cell potentials there. What we're going to do is we're going to do that formula where it was just the cathode minus the anode, and all we have to do is subtract them, okay? So that's exactly what I'm going to set up. I'll start off with putting the cathode first, subtract that from a negative anode because that's what we had, and then always making sure that those negatives, those two negatives that are being multiplied actually become a positive. We'll add those two together, and our E of our cell, or our standard cell potential, is then this value. So something else that I would like to note before we even move on to this is, and I'll get to it again, but it's really important to know that in a galvanic cell, as we mentioned before, and everything that I'm talking about is based on that, has to be spontaneous, right? For the reaction to actually occur, it must be spontaneous. And by occur, I mean occur on its own without us having to add any additional things like heat or a catalyst or so on. So that's something to note. And E of our cell, let me actually go back here. Let me see if I can go back real quick. One sec. We found that E of our cell was positive. That's just what I want us to look at. So since E of our cell was positive, that means it's spontaneous. Whenever E of our cell is positive, it's spontaneous. Whenever it is negative, that means it's non-spontaneous. That is going to be very, very helpful to know, so make sure to write that down. I have seen that as a trick question before, or just they might even ask you, they might actually give you a question like this and ask, is this a spontaneous or non-spontaneous reaction? And you just have to figure out what the standard cell potential is. And if it's positive, it's spontaneous. If it's negative, it's non-spontaneous. And then you get the question right. So that's pretty much all there is to it. Okay, let's do another type. So instead with this one, let's say if we were asked to find the standard cell potential. And what I want you to notice is they don't initially tell us that this is oxidation, this is reduction. We don't know which one is the cathode. Sorry, which one is the, actually, no, we don't know either. We don't know which one is the cathode or which one is the anode. Instead, we're given, both of these half reactions are given in their reduction form. So there's a trick to this. And by the way, how I knew that this was in its reduction form, remember your electrons will be added on the reactant side for reduction reactants, right? So that's how you can tell. Now, the trick with this is to figure out, okay, I need to figure out which one's the anode, which one is the cathode to actually do cathode minus the anode. And how you can figure this out is just looking at the potentials that were given, the cell potentials that were given from our table. The more negative the cell potential is, that makes it oxidation, and vice versa. The more positive it is, then that makes it reduction. So that's how I knew that this top one must have been the anode. And then, like I said, the more positive the cell potential, then that must make it reduction. So this bottom one is the cathode. And then from there, you don't have to switch anything. You don't have to move anything around. Since they're just asking for the standard cell potential, all you have to do is now take these values, subtract them from each other, and our answer is then the 0.21 volts. That is your standard cell potential. So I have seen that on different tests before, so definitely beware of that. That is a trick question. And then, like I mentioned, this is extremely important to note. This I also see you having to know on your test or AP test, any sort of quiz or test, okay, or even your homework. So this is going to be very, very important. All right, let's move on to cell notation. I've heard of it so many different ways. Line notation, cell diagram, they all mean the same thing, okay? All right, so what we're going to see is the cell notation is essentially a way to write the overall redox reaction, kind of like condense it down, to write it in a smaller way, and it's the shorthand way. That's essentially it. So what you're always going to see is you're going to see the anode on the left and the cathode on the right, like we saw before. And then in the center, there's a double line, which is representing the salt bridge. So let's say if we brought back something like this, this is our original one that we had before. And what we would see is our anode that we found, right? These were the half reactions that we found previously. But our anode is going to be on the left, and here. Our anode is going to be on the left, and we're going to start off with whatever reactant we have. So that's the copper in its solid form. By the way, don't worry too much about this right now. Let's just say that was given to you. If all this is stating is that it's an aqueous solution, and we were given the concentration of 1 molar solution. Okay, that just means molarity. So I'm just continuing on with that copper 2+ on the product side. And what I also want you to note is that single line means a phase change, meaning it went from a solid to aqueous. Okay, so that's essentially the concept there. And you could also think of it as like this arrow, like just stating, oh, okay, this was our reactant, this was our product on the anode. And then same goes for the cathode. You'll note that, okay, now we have our reactants and then we have our products, right? So that's essentially the concept there. And as mentioned, that double line in the center is our salt bridge, and that's exactly how you would write this. Okay, so that's the main thing for a typical redox reaction. The next one that I'm going to do is going to be something that has a different electrode, and let me get into that. So let's say if we had something like this. This setup is a tiny bit different, where we have something called an inert electrode. So what I want you to think about, all it's really stating is we can't have like a piece of metal. Like we have a different piece of metal, and I believe this was platinum. Yeah, platinum is a common one. Let me see if we have that. Yeah, we do. Cool. Right here. So a non-reactive platinum wire. Okay. So here, non-reactive platinum wire, that's essentially what we have. And I'm going to keep going with our cell notation, where our anode, which once again, they even provided right here, since that's our oxidation, that must be magnesium, phase change, or really just the products. This is representing our salt bridge. And then we have that H+, which is our reactants going to our products. And then lastly, they actually included whatever inert electrode there is. Okay, so a non-reactive platinum wire, that's where this goes. Any single time they add some sort of electrode that has nothing to do with it. Here it tells you it doesn't participate in the redox reaction. How you know this is the fact that it literally says it's non-reactive, and that it's not even part of it's not even part of the original redox reaction. Okay, so that's another way to look at it, but that's a potential test question as well if, of course, your professor went over it. Okay. So, see, someone said, Ayo, I'm super confused on assigning oxidation states. Yeah, and then Ryan saying, go to the beginning of the video. Thank you. She explained it really well. Yeah, so once this, actually, I think you can. Yeah, perfect. You can. Go to the beginning. I explained it there, as well as there's several of other redox notes that I did, so highly recommend checking that out as well. There's a discount code to shop my notes, and I go over a lot of examples there. Okay, so I'm gonna keep going. Okay, so I wanted now to get into how to find the cell potential. So now we're not looking at the standard cell potential. We're instead looking at just the cell potential. And what that means, again, it means it's under non-standard conditions, which essentially means it is not at 25 degrees Celsius. It is at a completely different temperature. So there are so many formulas that we have to see here. By the way, all the formulas that you see on the screen, you can find in the chemistry survival guide that I made for you guys. It's a gift. It's my gift to you. It's completely free. It's in the description box of this video and really every video. And I can put that in the chat right now. So all of these formulas are in there as well towards the end. That's where General Chemistry 2 or some of the AP chemistry formulas are. Just so you guys don't have to flip through your book or flip through your notes. It's all in one document. Okay, so something that I wanted to go over, because there are so many formulas. The main ones that we're going to focus on today are for Gibbs free energy, and same with the Nernst equation. Okay, so these two are actually the ones that I'm going to be focusing today on. I really went over this one, right? That helps us figure out the standard cell potential. And then you'll note that there are several different cases that can actually figure out what the standard cell potential is. That is dependent on whatever you're given initially. So I've seen this before. I believe it's called a concentration. Yes, it is. It's called a concentration cell. All that's essentially saying is we're going to use some sort of concentration. So meaning they have to provide us with molarity, or how much is actually in the solution, right? What the concentration of our solution is. So that's why you're going to see K or Q throughout all of these, okay? So we'll go over one with Q just in case you're not sure how to figure them out, okay? Same with N. N is something to really know. N is always talking about the electrons that are being transferred. So really the electrons that are being gained or lost, that is going back to the half reactions, right? Half reactions there, we were able to figure out how many electrons that we overall had. So that's what I want to center in right now. We're going to go over, let's go over two more examples. Perfect. And the Nernst equation is something we're going to go over. Okay. So first example, we're going to find Gibbs free energy, the change in Gibbs free energy. And this is under standard conditions. How I knew that, right, was just because of this little degree symbol, right? So that tells us it has to be under 25 degrees Celsius, and we'll use the proper formula accordingly. So now they're telling us for the following reaction and determine if the reaction is spontaneous. Okay. So they give us this overall reaction. First things first that we always want to do is we want to find E of our cell, so our standard cell potential. How we're going to do this is by figuring out our half reactions. So we have to figure out, okay, what do we have? Well, we have our anode, and I think we got practice of doing that already, where we have our anode, we have our cathode. We would have looked up using the standard reduction potentials table that they gave us. We would have looked up these values. And then the next step is just to subtract, right? So we'll subtract cathode minus the anode to get that overall cell potential, so standard cell potential. Okay, next. The next thing that we want to look at is we need to convert this to the proper unit. We're going to be using something known as Faraday's constant. So that is has specific units, and it actually has something called coulombs. All that is a fancy word for a way to kind of measure this type of electrochemistry types of, it's a different way to write volts, okay? There's a lot to it, I know. But a different way to write volts is actually joules divided by coulombs, okay? So all I did was I literally just changed this V to joules over coulombs, and now it's in the proper unit that I need, just so it can cancel and give me the correct value, all right? All right, let's keep going. I'm going to use this formula to figure out our change in Gibbs free energy under standard conditions. And we found E of our cell. So N is equal to the moles of electrons found in half reactions. All right, so electrons, all this is essentially saying, right, the half reactions that we talked about previously, we found that there are 2 electrons on either side, okay? That's all it's talking about. So those are the 2 moles of electrons, and that is found in your half reactions. That's why it's so important to know how to figure out, your electrons, which we talked about in the beginning. All right, and then for everyone who's talking about balancing equations or even balancing redox equations or redox reactions, I did that in the very beginning, so make sure to go in the beginning to check that out. And let's see, let's keep going with this. Okay, this is Faraday's constant. So this is essentially one of the forms that you might see it in. It's going to be coulombs on top and then moles on the bottom with electrons. Okay, so this is essentially what we're talking about. And that's why N has to be in this unit of moles times electrons. This is what we found previously. And I'm just going to plug everything in. So as stated, we have 2 moles of electrons. This initially was negative. I found the 2 moles of electrons based from the actual electrons we had in our half reactions. And then next, this is Faraday's constant. So this is F. And then E of our cell, standard cell potential, is what we found initially. I wanted all of these in the proper units so they can cancel. And our moles times electrons cancel, our coulombs cancel, and we're left in joules. So remember that Gibbs free energy is measured in joules, okay? So that's something I want you to just know that it must be in joules. And that's why everything cancels out. The next thing with this question was, is this spontaneous or not? Okay, so this is going to go back to something being positive or negative that we kind of were talking about before with our standard cell potential. This is non-spontaneous because Gibbs free energy is positive. All right, so when Gibbs free energy is positive, it is non-spontaneous. When it is negative, then it is spontaneous. Okay, and we'll go over a table. I think I have that here. Perfect. This table is going to be a lifesaver. So definitely, if you need to screenshot it or write it down, please do. This is going to be very, very important. Now, the reason for this is because this is going to help you figure out whether something is spontaneous or non-spontaneous. Once again, what this all means. Something is spontaneous means our reaction, those reactants that are in the very beginning, those two actually react on their own, and then they allow us to form our product. All it's stating, okay, our reaction occurs on its own. If something is non-spontaneous, the reaction does not occur on its own. Okay, so that's essentially the concept with this. As I mentioned, Gibbs free energy when it's negative, our standard cell potential when it's positive. Both of those make something to be spontaneous, and vice versa. This is then non-spontaneous. All right, those are just common questions. All right, and this next question. So we need to find the cell potential. And what we're going to do, we'll note this in a second, is the fact that they're actually stating just cell potential and they're not stating standard cell potential. This tells us or clues us in that we most likely have to use a different formula, that it's not going to be under standard conditions, right? So this is not under standard conditions. And I can tell that just by the fact that it didn't say standard. So I know I am solving for E of the cell. Okay. I have to use the Nernst equation because it's not going to be under, standard conditions. So I'll be using this formula. This is our Nernst equation. So now what I also want you to look at is I need to figure out what our E of our cell is still under standard conditions, okay? That's still something I have to do, and it's pretty much with all of these questions. So you're going to get a good practice with doing cathode minus the anode and figuring out which one is the anode and the cathode. So that's exactly what I'll do real quick here. I know you guys already kind of dealt with that. Let me go over this actually, because there is a little bit of a difference here. So remember when we were talking about balancing redox reactions in the very beginning, we talked about the fact that you have to balance out your electrons. So our electrons are not balanced here because here we have 2 and on the other one we have 3. So all you would have to do is multiply this top one by 3 and this bottom one, whole reaction, by 2. And there we will actually get the correct amount of electrons. They'll be the same, which is essentially the concept of balancing them. So that's exactly what I did here. I distributed that 3 to each. I distributed this 2 to every single one of these coefficients in front. And then that's what you're going to see here. So this is just the, a quick way of doing it. And then now you'll see that our electrons would then cancel. We'll add everything together. This should be gone. So we'll add everything together and we'll get this big, long redox reaction. Okay. So that just allows us to see what's going on. It is very important to do this. The reason why you want to do this is because this allows us to figure out what Q is. All right. So this is a trick question again, is in the case that your electrons are not balanced, you need to balance them first and then move on to finding Q or K. All right, so that I really want to make a strong point on that and make you guys, aware of that, just because I don't want you to miss anything on your next exam. So now what we're going to do next, so this is our anode, this is our cathode. How we knew that again, right, was just the fact of our oxidation numbers and the fact that our electrons, whenever our electrons are on the product side, that tells us it's oxidation. Whenever our electrons are on the reactant side, that's reduction. Okay. Before I move on to finding Q, let's find E of our cell. All we did was we subtracted our cathode minus our anode, and we got that 1.34 volts. Okay. Step 2, find Q. So Q is called the reaction quotient. This actually is covered a little bit before, move on to this. This is equilibrium, if you haven't seen this just yet, but this is really just a reaction quotient. All it's talking about is it's talking about concentration. Okay, so it's talking about our products are on top and they're going to be raised to some sort of exponent, and that's going to be the coefficient in front. It'll make so much more sense once I actually do this. Okay, so now, and then the reactants are going to be on the bottom, raised to a coefficient. All right, so raised to some sort of exponent. So this is what we had before. This is what we found previously. What I want you to think of is these are all of your products, right? However, for a quotient, for a reaction quotient, we don't care about solids. We don't care about liquids. We only place aqueous solutions, okay? So we're only going to be placing these aqueous solutions. So once again, this is out. So, and these two are in because they're aqueous. So that's what's going to be left in the reaction quotient. Okay, so then here, that's why this is the only one on top, right? That's the only one on top. That's what I meant by products. It's going to be raised to the coefficient, that coefficient of 3. That's why we have this exponent here. And then next, our reactants are on the bottom. So I'll have this one on the bottom, and we'll see our coefficients being the new exponent. Same thing goes for this H+, right? And its new exponent. So that's essentially how you're going to write your Q. Next thing is I'm going to go back to kind of like the beginning where we saw we were given concentrations initially. So all we have to do is actually plug in the values of all the concentrations that we had. So copper 2 plus had that 0.010, which is now, I'm going to substitute that in here. Same thing goes with this. I'm going to substitute this with 2, substitute this with 1, and so on. So and do the math from there. So after we do the math separately, this would have given us this value for Q. All right, so this is our value for Q. Now I can start plugging more things in. So now I'm going to plug everything into the formula. I'm using this formula again. We found E of our cell, and let's go over this. We found E of our cell, and then we also, the standard E of our cell, and then we found, actually this was given, something to note here, the 6, remember that 6 was just the amount of electrons that after we balanced everything out. That's why it is really important to do, since it can change the entire answer. You always want to make sure that your electrons are balanced, and we found that that was 6 on the bottom. This was our Q. After we plug this into our calculator, by the way, I'm going to make a note. Always do log first, then multiply by this value, or you could have done divided these and then times log of this value. I just don't put this all in your calculator. It tends to, get a syntax error, just meaning it doesn't calculate it correctly. And then E of our cell is then 1.41 volts, and that's our final answer. So that's how you find your cell potential under non-standard conditions. Whew, all right, we went through a lot. And thank you guys for, being here. I've seen a lot of good questions and people answering. Thank you, Brandon. So if you guys want your questions answered. So what I actually did, how this lesson came to life and came to be, was because Ryan actually asked me on Twitter to do this. So he tweeted at me his chemistry question because he wanted a lesson of electrochemistry. So that's exactly what I looked at. I highly, highly, highly recommend to tweet me your chemistry question, and you'll see on the screen how to do it. Make sure to actually tweet me at Hello Melissa M and use the hashtag AskMelissaMaribel just so I can actually see it. And tweet me your chemistry question, even if it's just the topic that you want me to go over. This is all for a chance for me to answer the question, of course. So I haven't been getting too many questions, and take that as an advantage right now, guys, because that means that I would probably do your lesson. I would actually make a custom lesson just for you, which I mentioned is worth over $100 this is really free tutoring. All right, so take advantage of this. I want you to get your questions answered. So make sure to tweet me throughout the week. And as you tweet me, of course, the next live, I will be then announcing, what topic I will be going over. And I also let you guys actually know ahead of time if I'm choosing your topic. All right, so Ryan said, yes, other people need to tweet their questions. I feel really spoiled. You are a little bit, no, just kidding. No, but I'm happy to help. And I'm really glad that I did this topic. I don't have a video on this just yet, so this is perfect in case anybody, needs help with electrochemistry. And this is always a cool concept to also think about. So, and you had really good questions. Tell us about your YouTube award. Sure. Real quick, guys, if you aren't familiar with my announcement that I just announced, I got accepted, or actually I won something called YouTube Next Up, which is extremely humbling and exciting. What it pretty much is it's a creator camp where creators come all together to learn from professionals, YouTube professionals. They have mentors. The mentors are YouTube pretty much people who have already gone through this and are successful. So they have thriving YouTube channels and have even created a business out of this. So I'm really excited to be a part of it. It's pretty amazing. I actually just put to kind of talk about more about it. There's a publication that YouTube did, and I'm on there. Woohoo! So yeah, that's what they're doing now this year. They're actually doing specifically, I believe, YouTube Latino, which is me, right? So that's where I'm part of. If you guys aren't familiar with my story, I have it on my Instagram. I am Latina, and I'm so thankful to represent that, education and the fact that I am Latina as well. So they have a lot of different ones. I start the program September 17th, so very, very soon. It's really exciting. And if you actually want to, if you want to see kind of like behind the scenes of literally the YouTube space in LA, make sure to follow me at my Instagram, which is Hello Melissa M as well. So I'll see if I can put that link in the chat as well. Ryan says, so cool. It's so well deserved. Thank you. I appreciate that, guys. Been working at this for actually a year, a little over a year. So it's amazing to actually see that we won, and I really appreciate your guys' support, because the requirement was to actually get to 10,000 subscribers, and I barely made that cutoff when I applied. So that was really awesome. Really, really awesome. So yeah, if you guys want to see the behind the scenes of that program and kind of follow me through that journey, I'm really, really excited. I really got the schedule, and I actually met a couple people already, so that's going to be awesome. And yeah, so make sure to, once again, guys, tweet me if you want to see what in the world I'm up to. And thank you, Brandon. I appreciate that. To see what other things I'm up to on Instagram. I always have stories going on. That's kind of more about me rather than just chemistry. That's more of this channel. But yeah, make sure, guys, to tweet me your questions. I want to help. So awesome. And I'm excited. I'm excited for the next one, guys. So I hope you guys have an awesome, awesome Sunday and have an amazing week as well. So I hope to hear from you guys with your tweets. And yeah, just have a great Sunday. All right, guys, I'll see ya.